Hello students. In our previous video, I discussed how we can draw the Lewis structures for various species, and then based on the Lewis structure, we can determine the number of electron domains around the central atom. This is very important because determining the number of electron domains around the central atom will dictate what kind of arrangement they take in 3 dimensions. And just as a review, Lewis structures do not show any 3-dimensionality. Everything is drawn as being in 2 dimensions. There are no wedges or dashes showing any 3-dimensionality. But these chemical substances do exist in the real world, and they exist in 3 dimensions. And many of them actually do take advantage of the 3rd dimension to get the electron domains, or these electron regions, further away from each other, because we know in the VSEPR, the valence shell electron pair repulsion theoretical model, these electron domains are trying to get as far apart from each other as possible. So based on the number of electron domains, that is going to dictate what kind of geometrical arrangement these electron domains are going to take. As I mentioned in the previous video, we're going to be dealing with the number of electron domains when we have between 2 and 6 electron domains around a central atom. So on this chart, I've given you 3 columns. The first column is for the number of electron domains. And so we're just going to enter these numbers. 2 electron domains, 3 electron domains, 4 electron domains, 5 electron domains, and 6 electron domains. And this is going to give us the 5 electronic geometries that we're going to encounter in this class. The second column is for the name of the electronic geometry. And so I will fill that in last. We're going to sketch the electronic geometry first. Now to sketch the electronic geometry, I am going to use the letter A to represent the central atom. There's my central atom right there. And if I have 2 electron domains, they're going to try to get as far apart from each other as possible. And that means they're going to arrange themselves on opposite sides of the central atom to get as far apart as they can. So right now, I am just drawing a single line here, and we know that that typically represents a single bond with 2 shared electrons. However, I'm just doing that so that we can see the direction in which they are pointing. This is intended to represent right now any kind of electron domain. So it could indeed be a single bond, or it could be a double bond, or it could be a triple bond, or it could be a lone pair of unshared electrons, or it could be that rare case where I have a single electron that's unshared. But for now, to simplify these diagrams and to make the sketches easier to understand, I'm just going to use the single bond as an example of an electron domain. So I have an electron domain of some kind pointing out on this side, an electron domain of some kind pointing out on the other side. And we can see that this forms pretty much a straight line as I look at the electron domain geometry. We know that the angle between these, if this is a straight line, the angle would be 180 degrees. And the name of this electronic geometry is therefore called linear. And here is an example of it using a model. I have a central atom, that's this one right here. And then I have some kind of electron domain off to the right, some kind of electron domain off to the left. And notice that they are all in the same plane. They form a straight line. So I don't need to show any wedges or dashes to imply that these electron domains are somehow moving out of the plane of the paper. They're all in the same plane, and they form a straight line. The next electron geometry arises when we have 3 electron domains. And when we have 3 electron domains, those electron domains are going to try to get as far apart from each other as possible. And so the geometry, you can see all 3 electron domains are in the same plane. It's a flat plane here. But they are arranged equidistantly around the central atom. And so, to draw that, We draw the central atom, and then 3 electron domains spaced evenly around that circle. And we know that if you have 3 divisions of a circle, 360 degrees are divided into 3, therefore the angle here is 120 degrees. And remember again that I'm just using single bonds here to make this easier to see, but these could be any kind of electron domain. This could be a double bond, a triple bond, a lone pair of electrons. And I think that you can see that if we have formed this triangular shape and they are all in the same plane, notice how they're all in the same plane with each other, then we are going to have the name trigonal, which is our word for triangular, trigonal, planar, because they form a triangular or trigonal arrangement all in the same plane. Okay? That's for 3 electron domains. The electron geometry is trigonal planar. We're going to continue on. What if we have 4 electron domains? Well, at this point, we start to have to use the 3rd dimension. So I'll point this, I'll arrange this so that you're looking from the top of this electron domain. And you can see how the others are arranged triangularly, trigonal, in a trigonal pattern. But when I move it down, you'll see that they are not in the same plane as each other. See how this one comes down, down, down? So they are not in the same plane as the central atom. And I appreciate that this is a little bit hard to see on a video. But if I move it back and forth, you can see that there are 3 electron domains that are arranged so that they are pointing down a little bit and one pointing up. In fact, all of these positions are equidistant from each other. I can make this one the top one. And you can see that I still have the same arrangement. Or I could make this one the top one. So these are all equal positions. They're all equidistant from each other. Okay? And if I set it on the paper, you can't see it from here, but there's a little bit of space underneath where it's obvious that this blue central atom is not sitting on the paper. So these are not all in the same plane with each other. They're taking advantage of the 3rd dimension in order to get further away from each other. Now we call this arrangement a tetrahedral arrangement. So the challenge now we have is to represent this on paper. This is a 3-dimensional shape, and we need to represent it on paper. So now we are going to use wedges and dashes to show some 3-dimensionality. So I'm first going to draw the central atom. And if I hold this structure just like that, you can see a little bit how I'm going to do this. There's the central atom in blue. And you can see that this top electron domain is sticking straight up from it. So I'm going to put that, keep it in the plane of the paper, keep pointing straight up. That one right there. And you can also see that there are 1, 2 that are pointing toward me. And one's pointing toward me and down a little bit and to the right, and the other is pointing toward me and down a little bit and to the left. So the way that we do that, to the right and to the left, and I'm going to draw those as wedges. And the wedges imply that this is getting larger as it comes out toward you. So a wedge means the large end of the wedge shape is coming toward you. So that indicates that this right here is the large end of the wedge because it's closer to me. It's coming toward me out of the plane of the paper. I'll do the same on the other side. Make this a wedge because it is coming out of the plane of the paper and toward you a little bit. See, it's coming toward you a little bit. And then the last electron domain, the fourth electron domain, is going down a little bit, but it's going behind the central atom, so it's going into the paper. It's going behind the plane of the paper. And the way that we show that is we do these dashed lines that get smaller and smaller and smaller. So the dashed lines getting smaller and smaller and smaller shows something fading away from you as it goes into the distance. So the wedges show something coming toward you a little bit. The dashes show something fading away. And that's how we represent this three-dimensional structure in only 2 dimensions. We use these wedges and dashes. Wedges and dashes had not been needed up here because these were all in the plane. Those electron geometries were all planar. But this one requires three-dimensionality to be shown. So what is the angle here now between these electron domains? Well, if I hold it like this, you can see it's a little bit more than 90 degrees, isn't it? In fact, it's 109.5. degrees. And again, this is difficult to show in a video or on 2 dimensions. In the class or in lab, we would get out the model kits and we would have you build these so that you could actually get your hands on them and work with them in 3 dimensions. And that would help you get a better sense of the 3-dimensionality of these structures. But we can't do that just on video. So at the end of this video, I'm going to be linking 2 other videos, and they will take advantage of some 3D animation. And if you want to watch those, you can get a little bit better sense of how these look in 3 dimensions. Okay? Tetrahedral electron geometry. Moving on to 5 electron domains. 5 electron domains is basically a combination of the 2 and the 3. So now we're going to take the 2 and it's going to be up and down, and we're going to take the 3 that are arranged equidistantly. And what we're going to do is I'm going to take these 2 and make them up and down. So now I have my 2 that were up and down from the linear, the 2 arrangement, and I've added them to the 3 from the trigonal planar arrangement. You see that? My 2 from the linear plus the 3 from the trigonal planar arrangement. Okay, so there's 5 of them. Another way of thinking about this is you have the planet Earth, you have a North Pole and a South Pole, and then 3 arranged around the equator, right? You see that? North Pole, South Pole, 3 around the equator. And the 3 around the equator are arranged equidistantly. So how am I going to write that? How am I going to draw that? I have a central atom, I have a North Pole and a South Pole, and they are in the plane of the paper. For the 3 around the equator, I'm just going to arbitrarily pick one of them and put that in the plane of the paper as well. So I'll make that one in the plane of the paper here. And that leaves the other 2 equatorial positions pointing out to my right a little bit. And one is pointing away, and one is pointing toward me. And you can see how if I put them like this and just look at them straight on, I can't see the one that's behind here. It's hidden by this one. So I'm going to cheat a little bit and cant it forward just so that I can see the one behind. So there are 2 coming out on the right, one coming toward me and one going away. 2 coming out to the right. One is a wedge because it's coming toward me, and the other is a dash because it's fading away behind the paper. So there we go. We have my three-dimensional structure there. What are the bond angles? Well, they are the bond angles that were in my 2 and 3 electron domains. So right here, I have between the equatorial positions, I have 120 degrees because that's similar to the trigonal planar around the equator. And then from the North Pole to the equator, I have a 90-degree angle because that originated from that linear arrangement of those two. So there's a 90-degree. This is a trigonal, that is a triangular arrangement around the equator, bipyramid. And the reason it's called a bipyramid is if you look from the equator to the North Pole and I connected these dots, I would form a little pyramid. That would be the top of the pyramid, and these equatorial positions would be the base. I would form a little trigonal pyramid there, a pyramid with a triangular base. And if I look at the South Pole, I could do the exact same thing on the South Pole. I could make another pyramid with a triangular base. Well, when you have two pyramids and their bases are fused together, you have what's called a bipyramid. And they have a triangular base, so it's a trigonal bipyramid. A double pyramid with bases fused, here's one going up and here's one going down, and their bases are based on 3 points or a triangle, so it's a trigonal bipyramid. And that's the electron geometry when you have 5 electron domains. Now we're going to move on to the fifth of our electronic geometries, and that is when we have 6 electron domains. And this is what it looks like. 6 electron domains is very similar to 5 electron domains. 5 electron domains has a north pole, a south pole, and 3 around the equator. 6 electron domains has a north pole, a south pole, and 4 around the equator. And once we get to this arrangement, north pole, south pole, 4 around the equator, all of these positions are equal. So I could take this and that's my north pole, or I could take this and that's my north pole, or I could take this one and that becomes my north pole, or I could take this one and that becomes my north pole. So you can see that I have a linear arrangement of 2 of them, north pole, south pole, and 4 arranged equidistantly around the equator. This is how 6 electron domains arrange themselves to get as far apart from each other as possible. So how do I draw it? Central atom, north pole, south pole within the plane of the paper, so they're not drawn as wedge or dashes. Now I'm going to have 2 on the right that look very similar to the 2 on the right up here, where one's coming toward me, one's going away, both on the right. So there's my wedge coming toward me. There's my dashes going away. And now I'm going to do the exact same thing for the left. I've got one coming toward me and one going away on the left now as well. Okay, there's the 3-dimensionality of that. And now all of these angles are 90 degrees. You can see that's a 90-degree angle right there. Between the equatorial positions, they are also 90 degrees. So those are all 90-degree angles. Now the name for this is called octahedral. And that may seem a little bit non-intuitive. Why are we calling it octa, which means 8, when we have 6 electron domains? Well, that's because if I connected all of these points, then I would create a solid that has 8 sides. So I'd have a side here, 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 and here in the north hemisphere. I would have 4 sides, and I would have four more in the southern hemisphere. 6 electron domains is an octahedral electronic geometry. And again, because it's difficult to see this in 2 dimensions or on a video, I'm going to link to 1 or 2 videos here at the end of this video so you can see some 3-dimensional animation that may help you with these. Otherwise, if you can get your hands on a model kit like this and start to build these models, it will also help you visualize these shapes as well. One last thing, these are the electronic geometries. These are not molecular geometries. That comes next after this. But right now, these are electronic geometries. These are the arrangements that the electron domains take. And in the next video, we'll start talking about what's called molecular geometries, which is another word for the shape of the molecule. And that starts to look at the bonded atoms that you have on here. But right now, we're just looking at the electron domains. And I've used a single bond to represent any kind of electron domain, though it could be a lone pair of electrons, it could be a triple bond, single bond. I've used the single bonds here to represent any kind of electron domain.